If you are building payment systems in .NET, this is what failure looks like: a continuous, unbroken stream of hexadecimal characters pouring over a TCP socket connection from a declined transaction. Modern developers expect to read data in JSON, a format where every value comes neatly packaged with a descriptive label. Banking switches operate under much stricter constraints. To connect to the national payment grid, the Central Bank of Nigeria and the NIBSS mandate the ISO 8583 standard for your front-end processor. A front-end processor, or FEP, is the gateway server routing transactions between a bank's internal network and the central switch. ISO 8583 is not an object. It is a strictly positional, byte-level protocol. There are no keys, no tags, and no delimiters. In this format, the exact location of a byte dictates its entire meaning. To build a functional C# FEP, you have to reverse engineer this continuous byte stream into discrete data points. That process starts with the very first 4 characters. This diagram isolates those first 4 bytes. They form the message type indicator, or MTI. The MTI categorizes the intent of the payload. A value of 0200 indicates a standard financial transaction request, while 0100 signals an authorization request. The MTI tells the switch what the message is trying to do. It provides 0 information on how to slice up the hundreds of undelimited bytes following it. This diagram isolates the 16 characters immediately following the MTI. This string is the primary bitmap. This 16-character string is the protocol's engine, but in hex, it's unreadable. The first mechanical step in C# is converting it into a 64-bit binary sequence. We map those characters into a strict grid of 64 ones and zeros. Each position corresponds to a data element. 1 is included, 0 absent. Bit 1 indicates a secondary bitmap. Here, it's 0. Bit 2 represents the primary account number. Because it's 1, the card number is in the data block below. Bits 3 and 4 operate on the exact same logic, checking for the processing code and the transaction amount. The bitmap functions as a highly efficient self-indexing checklist. It saves the parser from guessing what data the network actually sent. Knowing which elements are present solves half the problem. The parser now needs to know exactly how many bytes to read for each one. This schematic shows a fixed data element. Data element 4, the transaction amount, is strictly defined as N12, 12 numeric characters. The logic simply counts out exactly 12 bytes and extracts them. Fixed elements are mathematically safe. The parser is hard-coded to take that exact length every single time. The mechanical risk increases with variable data elements. Data element 2, the pan, is an LLVAR. LLVAR means the length varies, defined by a 2-digit prefix preceding the data. In this diagram, you can see the 2-step parsing mechanic sign LLVAR. The parser must first read the 2-byte prefix to determine the length of the card number, and only then expand to slice the subsequent characters. Longer data fields use an LLLVAR structure. They rely on a 3-byte prefix to declare their length before the actual data begins. If your C# logic misreads a variable length by a single character, it creates a cascade effect. Every subsequent data element is read incorrectly. One miscalculated offset corrupts the entire downstream parse. The resulting data becomes unreadable, and the NIBSS switch will immediately drop the connection. Manually writing bit-shifting logic to calculate these offsets in C# is fragile. In a production environment handling live funds, manual parsing is a liability. Robust FEP implementations utilize specialized libraries like NetCore 8583. These libraries automate the bitmap mathematics and offset calculations. The architecture of these libraries relies on 2 core components: the message factory and the parse map. This side-by-side view shows how a parse map operates. The developer writes an XML or programmatic template mapping each data element index to its specific isotype, like numeric or LLVAR. When a raw byte array arrives over the socket, it is fed into the message factory. The library automatically executes the hex to binary conversion and cross-references the result against your parse map. The library successfully transforms the hostile byte stream into a strongly typed C# ISO message object, containing completely safe, validated values. By abstracting the byte-level iteration into a mapping template, the developer is freed from low-level parsing logic to focus entirely on authorizing the transaction. The lifecycle of the payload is strictly linear. The socket delivers a byte stream, the MTI declares the function, the hex bitmap provides the binary checklist, and the C# parse map defines the extraction boundaries. The version of ISO 8583 mandated by the CBN and running modern Nigerian banking was standardized in 1987. This decades-old protocol survived because it is highly optimized. It is self-indexing and consumes minimal bandwidth compared to modern JSON payloads. The global financial sector, including Nigeria, is slowly beginning the migration toward ISO 2022, a standard built entirely on XML. Until that migration is complete, mastering the 1987 bitmap index remains the mandatory bedrock skill for any payment engineer in the region. It is the gatekeeper for millions of daily transactions.